Hi, today we look at Schmidt orthogonalization method. Schmidt orthogonalization method. This is a method which converts a non-orthogonal set of linearly independent functions into an orthogonal set. Okay. A non-orthogonal set of linearly independent functions are converted into an orthogonal set over an arbitrary interval and with respect to an arbitrary weight or density factor. So this is a method which takes a set of non-orthogonal linearly independent functions and forms a set of orthogonal functions over an arbitrary interval and with respect to an arbitrary weight or density factor. Okay, so this is a very important method. So let's first look at what is meant by orthogonality of functions with respect to some weight function. Okay, what is meant by orthogonality? Actually, we have seen this in the last class. If two functions are there, ui and uj, and if their inner product you represent like this, ui comma uj, which is integral a to b ui conjugate x wx uj x dx. If this is equal to 0, if this inner product is equal to 0, we say the two functions are orthogonal with respect to the weight function wx. Okay, so this is what is meant by the orthogonality. The orthogonality is that. Now the normalization. Okay, normalization, what is meant by, let's look at what is meant by normalization of a function. A function phi a of x, this is said to be normalized. This function phi a of x is said to be normalized with respect to weight function if integral a to b phi a conjugate x wx phi a of x dx that is equal to 1. See, phi a conjugate x phi a x dx equal to 1. Or we can say if phi i inner product of phi I with phi I, if it is equal to 1, we say the function phi I is normalized. The function phi I is normalized. Okay. And if phi I is real, okay, then phi I conjugate means complex conjugate, that will be equal to phi I. There will be no change in phi I. So this equation can be written integral a to b phi a square wx dx that is equal to 1. So inner product of a function with itself is equal to 1, we say that function is normalized. Okay, now let's look at orthonormal functions. What are orthonormal functions? Suppose we have a set of functions phi 1, phi 2, phi 3, etc. Such a set of functions are there, and for any two functions phi a and phi j, if integral a to b phi I conjugate x, w of x, phi jx dx, that is inner product of phi I with respect to phi j. This is what? This inner product of phi I with phi j. If that is equal to delta ij we know that is a Kronecker delta. If I equal to j, its value is 1. If I not equal to j, the value is 0. So that means if the two functions are different, this integral, which is the inner product, that will be 0. And same function, this will be equal to 1. So if you take such a set of functions, they are normalized, these functions are normalized, and they are orthogonal as well. Okay, so this is an orthonormal set. And in Gram-Schmidt orthogonalization method, we can actually form an orthonormal set from a set of linearly non-orthogonal linearly independent functions. Okay, now how do we normalize a function? If you divide a function by its norm, that is root n. Okay, so phi I equal to psi I by root n, then phi I will be normalized. Suppose psi I is unnormalized, and if you divide it by root n, you will be getting the normalized function. So the idea is this: suppose we have integral a to b psi I square wx dx, that is equal to n. That is equal to n. You are not getting 1. That means this is not normalized. Psi I is not normalized. But if you write this n as root 10 into root 10, you have this integral a to b psi I by root 10 into psi I by root 10 wx dx, that is equal to 1. So that means this is normalized. Okay, this is normalized. So phi I, that is equal to psi I root 10. Okay. Now suppose we are going into this Gram-Schmidt orthogonalization procedure. Suppose we have a set of linearly independent functions unx, where n is 0, 1, 2, etc. So the functions are u0x, u1x, u2x, etc. Set of linearly independent functions are there, and orthogonalized. So these are non-orthogonal. Okay, these are not non-orthogonal. Okay, we have linearly independent non-orthogonal set of functions. Okay, and we can construct an orthogonalized set. Okay, we can construct an orthogonalized set. Okay, from this, and it is done using Gram-Schmidt orthogonalization method. Once we have set of psi n, finally we can form a set of functions phi n, which are normalized psi n. Once we have psi n with us, we can normalize, we can obtain phi n. Okay. So this is what we are going to do. We have un, which are linearly independent, non-orthogonal, they are unnormalized. Okay. From that, we form linearly independent, orthogonal, unnormalized function. And from this set, we form phi n of x, which are linearly independent, orthogonal, normalized. So that means we are forming an orthonormal set. Okay, we are forming an orthonormal set. Okay. So let's see what is the procedure involved. First step, what is it? We put n equal to 0. We have un of x with us, where n can take value 0, 1, 2, etc. So we put n equal to 0. So we have psi 0 of x, which is u0 of x. Okay, psi 0 of x. And this is the first function in the orthogonal set. The psi 0 is there, so we find phi 0. Phi 0 is normalized. So how do we normalize? You divide psi 0 of x by integral psi 0 square w dx. This is our n. Okay. We found we can normalize a function by dividing it with root n, where n is the norm. So we have this psi 0 of x over integral psi 0 square w dx to the power half. So we have the normalized one. Okay. Now what we do is we want to have the second function in the set. We put n equal to 1 and let suppose that we choose psi 1, the second function in the orthogonal set, as psi 1 of x equal to u1 of x. Okay, u1 is with us, plus a1 0 phi 0 of x. Phi 0 of x we found in the previous step. u1 of x is with us, is available to us. So we are choosing psi 1 of x as equal to u1x plus a1 0 phi 0 of x. Then we demand that this psi 1 of x is orthogonal to phi 0. Phi 0 we formed in the first set. So in the second step, we put n equal to 1 and psi 1 of x is chosen as u1x plus a1 0 phi 0 of x, where we demand that psi 1 of x is orthogonal to phi 0 of x. Okay. So that condition is taken here. Psi 1 is orthogonal to phi 0. So integral psi 1 phi 0 w dx, that is equal to integral u1 phi 0 w dx plus a1 0 integral phi 0 square x dx. Okay. So we take the orthogonality with respect to phi 0. So this is 0 and this value, this is 1 because phi 0 of x is normalized. This is equal to 1. So we get a1 0 as this. Okay, so this is a1 0. And once a1 0 we got, as we substitute here for a1 0, you get psi 1 of x. Okay, phi 0 x is known to us. We had determined it in the first step. a1 0 we now obtained. Then u1 of x is with us, so we have the psi 1 of x. So we get psi 1 of x and we just normalize it. Okay, we just normalize it. So phi 1 of x is equal to psi 1 of x integral psi 1 square w dx. Okay. Now the third step, we pick u2 and we form psi 2 of x like this, u2 plus a21 phi 1 of x plus a20 phi 0 of x. And as we did in the last step, we find a21 by taking this, that psi 2 has to be orthogonal to what? Phi 1. This is the condition. Psi 2 is orthogonal to phi 1 and we find a21. A20, that means the psi 2 is orthogonal to phi 0. Okay, and we determine a20. So a21 we determine, a20 we determine, and we have psi 2 of x now, which is u2 plus a21 phi 1 of x plus a20 phi 0 of x. So phi 2 of x, we determine psi 2 of x by its norm. So we have phi 2 of x as equal to psi 2 of x by this integral psi 2 of x square w dx. So we have the phi 2 of x. So we have phi 0 with us, phi 1 with us, phi 2 with us, and same way repeating like this, we find phi 3, phi 4, and we ultimately form an orthonormal set. So the general equation for obtaining the different psi 1, psi I, that is given by this psi I of x equal to uix plus ai 0, phi 0 of x like this, ai, this is ai, I minus 1 phi, I minus 1 x. So in that way we form psi I of x. Okay, and aij, how do we get aij? Integral ui phi j w dx. Okay, integral ui minus of integral ui phi j w dx, and appropriate limits will be there. Okay, so we get the aij. So we can have the psi I of x, and from psi I of x we can form what? The phi I of x. Okay, phi I of x. So this set can be formed. So this is the grand Schmidt orthogonalization method, and using this we are obtaining the Legendre polynomials. We obtain Legendre polynomials by the grand Schmidt orthogonalization. Actually, we are forming an orthonormal set from the set of functions un of x equal to x to the power n, where n equal to 0, 1, 2. So this is the non-orthogonal set with us. From this we are forming orthogonal set. Okay, the interval is minus 1 and 1. The density function is w of x, that is equal to 1. Okay, so what are the functions with us? The functions are u0 equal to 1. Okay, then u1 equal to x and u2 equal to x square, like that. Okay, and u3 equal to x cube. So these are the functions. Then we know u0, that is equal to the first step, u0, we know x to the power 0, that is equal to 1. So phi 0, you know, that is u0 by integral, these are the limits, minus 1 to plus 1, u0 square w dx to the power half 1 over minus 1 to 1 dx. This is 1 by root 2. Okay, so the psi 0 is taken as 1. Okay, this is taken as 1, which is equal to u0, and from that we find phi 0. Okay, this is psi 0. Psi 0 is u0 itself. So we have the normalized one, which is 1 by root 2. Then the psi 1 of x, that is u1 plus a1 0. Phi 0, u1 is x. Phi 0 we have got 1 by root 2, and a1 0 is this. Minus of integral minus 1 to plus 1 u1 phi 0 dx. Okay, and u1 is x, phi 0 is 1 by root 2. So this is minus 1 by root 2, x square by 2, limits minus 1 to plus 1. Okay, so this is minus 1 by root 2. As we apply the limits, we have this. So a1 0, we are getting it as equal to 0. a1 0 we have got it as equal to 0. So as we substitute here, this a1 0, now we have got it as 0. So psi 1x is x. Okay, so phi 1 of x is this, x over integral minus 1 to plus 1 x square dx. This is equal to root 3 by 2 x. Okay, so what is our psi 0? Psi 0 is 1. What is our psi 1? Psi 1 is x. So these are all Legendre polynomials. This is p0 of x and this is p1 of x. Okay, and the same thing we continue, and we have we have found psi 1 and we can obtain the psi 2. Okay, what will be psi 2? Psi 2 will be u2. Okay, u2 plus 82151 plus 82050. Okay, that will be our psi 2. So psi 2 will be u2 plus 82151 plus 82050. And then we find the what is it, the psi 2, and from psi 2 we find phi 2, and we continue this process. So we at least we find psi 0 3 functions. Okay, what is it, psi 0, psi 1 and psi 2. Okay, at least 3 functions have to be found out, and their corresponding normal set phi 0, phi 1, phi 2 has to be determined. Okay, at least 3 functions have to be found out. So this is how we determine or we obtain an orthonormal set from a non-orthogonal set. Okay.